In this final video, we're going to look at some applications of exponential and logarithmic functions. We'll do a little bit of math, but largely this is just going to be a framework of scenarios that you could be experiencing exponentials and logs in. And the first one is exponential decay. And we maybe have encountered this before. The idea is that in something that's decaying exponentially, you have an initial amount. That's what A0 represents. So we start with this amount, and then over time, it's decreasing at a quicker rate, or at a quick rate at the beginning, and then as time progresses, it's actually decreasing. It's still decreasing or going away, decaying, but it's decaying slower as time progresses. Okay, and so the equation we will see is that it's that base amount, and then we multiply by e, the natural number, to the minus kt, and so t is time, k is kind of what we think of as a growth or rate of growth or decay. Okay, and then typically if we express k, this whole thing needs to be a negative exponent, so k is typically a positive number. Okay, typically. And so what we'll see is that if k is a small value, so we're thinking like 0.0001 or something, like that's going to decay really quick or really slowly, versus if we have a very large k, so we're talking like 3-ish, that's pretty big when we're talking about exponential decay, then it's going to decay faster. Okay, so it's going to asymptote to 0 quicker. Okay, so some scenarios that you might encounter in this with this sort of exponential decay is drug absorption. Okay, so a lot of it's going to absorb. So you apply initial dose, it's going to absorb quickly, and then there's going to be a little bit left over time. Okay, radioactivity with compounds. Okay, so like uranium, plutonium, all those things are radioactive. Heat loss certainly is exponential decay. If we talk about music, okay, when loudness and like when you pluck a string of a guitar, okay, the loudness or the frequency of that is going to decay over time. Okay, and then lastly, fluorescence of a compound. Okay, so seeing how brightly things are over time, that's going to decay exponentially as well. Another one is radon, and this one is actually super common. And note for all of you, but when you are looking at buying a house, you should always make sure to check your house for radon. It is a radioactive compound, and it is harmful to you. So make sure to, one of the things that you can ask for in your house inspection is a radon inspection, and you can, it is a little spendy, but I mean, if you're already spending hundreds of thousands of dollars, why not throw in another little bit there? Okay, and as you can see from the map, Minnesota, yep, there's a fair amount of radon present in our area, so good thing to double check. Okay, okay, so anyway, we want to look at how radon decays over time. So we can pretend we have 1 million atoms of radon, and then here's the particular scenario that we're in. And so the first question is, how long does it take to reduce the initial number of nuclei? So again, atoms, nuclei, tomato, tomato, by 50%. Okay, well, I'll let you think about that for a minute, and then we have these other questions as well. Well, if we think about the first one, we begin with 1 million. Half of 1 million is 500,000, and according to the graph, that is exactly at 1 minute. Another nice thing is this little legend here. T of 1/2 is 1 minute. This T 1/2 is actually what we call half-life. And half-life, more formally, if you want to get this in your notes, is the amount of time required for 50% to remain. So that means after 1 minute there's 50%, and then when we look at 2 minutes, that would be half of whatever we had at the 1 minute mark, so that would be 250,000, 125,000. So it divides by 2 essentially every minute according to this model. Okay, so then what is the value of k? Now that's actually an interesting question. If we remember our base model, a is equal to a naught e to the minus kt, well, it was a of t technically. If we want to find the value of k, all we have to do is plug in some numbers. So a A naught was 10 to the 6th, 1 million. And then if we think about what happens after 1 minute, well, that would be k times 1. And then at 1 minute, this would be 5 times 10 to the 5th. Okay, and then now solving this is where the exponential equation comes into play. We would say, okay, divide by 10 to the 6th to both sides. And I end up with 0.5, if you rearrange it a little bit, is equal to e to the minus k. And now, hey, look, this is something that I can use the tattoo on. So I use the tattoo. Natural log, it'd be log base e of 0.5 is equal to negative k, or rather just slap the negative on the other side, make that positive. There we go, we found it. And we can punch this into a calculator if we want. And then how many nuclei are left after 4 seconds? Well, that just means here that t is equal to 4, and we would want to say a of t, or a of 4 rather, is equal to, we start with 1 million, and then we have e raised to the negative, and then k is our negative natural log of 0.5, so the negatives will end up canceling, and then we have multiplied by 4. And then this whole right side we can punch in our calculator and get a value. Okay, I'm not going to take time for that. For the last part, how much time does it take for having 90% of the material to decay? Well, that just means that if we start with 1 million, that means remaining, right, we would have 10%. So 10% remains. So I would have, my amount would be 0.1 times 1 million, or 100 million, right? And then this, and then times e to the minus negative natural log of 0.5. Okay, so once I find the k value, that doesn't change, and then I need to have t. I would have to then solve this equation for t, and we'll get a little bit of practice with that in class, hopefully. And when I say we get a little bit of practice in class, this is the next this is the exercise that we will see in class. So we'll get to this one in class. So let's not worry about it. But this one is talking about half-life. Okay, and so it says here's our exponential function. We have to determine half-life. So when we find half-life, that means it's the time that we need for a to be 1/2 of what we started with, right? So in my equation, I would just start this equation by saying a naught over 2 is equal to a naught e to the junk times t. Okay, I'm not going to write that all out, but that's how you would start this question. Okay, I want to get to the other examples. So exponential decay. Certainly a scenario where we would see exponential and logs, or exponential functions and logarithmic functions pop up. Okay, instead of decay, you can have growth. That would just be something like this, where we have population modeling. And so we would say this is exponential growth because we can see, okay, this is the world population, and you can kind of see when it started to take off right in the 1940s and 60s. Hence, that's why they call it the baby boomer generation, because the population surged. And so you can see kind of that exponential growth pattern, though, or exponential function pattern, where we're increasing quickly over time. And so then we can ask questions about this. Well, if we assume exponential growth, what will our population be? Or is this projection in the year 2100 accurate? Maybe, maybe not. Okay, so anyway, we can do population modeling. And the last thing we can do with this whole thing is look at spread of a disease if we use some key assumptions. So as you can see, this is from the movie Contagion. Really good movie, and it actually takes place in Minneapolis, Minnesota, so that's kind of another fun thing, I think, at least. So I'm not going to play the trailer for you just for time purposes, but go to Google or go to YouTube, search Contagion trailer, and then in there's actually a really nice exponential problem that we can solve. And so we'll try and pull that into class again if we have time. So that's going to be kind of all the information for for this video. No quiz in this video, but just some fun applications. So we'll see more of these in class.